In this video lesson, we're going to do some investigation of floating point on MCUs to give you a little broader understanding of this topic. So here's the outline, which I'll go through briefly. First, we'll look at the floating point assembly code generated by the GCC compiler. Now, you don't need to understand assembly code for this, and I think you'll find it interesting. Next, we'll look at measuring floating point performance to answer questions like how much faster is an FPU over doing the calculations in software. As part of this, I'll describe a very old benchmark program called the Whetstone. Then, using that benchmark, I'll give you the results I obtained running tests on several MCUs with and without an FPU. Then I'll give some prompts or questions followed by my take on the prompts, and finally a brief summary of the lesson. So now let's imagine the compiler generating machine code for floating point expressions in C. And the compiler will be told if there's an FPU or not, and what kind of FPU if there is one. So first, let's think about the floating point operations that are supported directly in the C language. And this includes things like addition, subtraction, multiplication, and division. And there are two cases to consider that the compiler has to deal with. First, if there's an FPU, then the compiler will generate machine language instructions that directly do the floating point operations. These are instructions that the FPU will execute. If there isn't an FPU, then the compiler generates function calls to software that does the floating point operations using the general purpose CPU. These functions are very low level, very tedious. I looked at them for the ARM processor, and they're written in assembler for maximum speed. Now for the second case, where the compiler generates the function calls, these functions are part of the C runtime library. This library is tightly coupled to the compiler and is normally used only by the compiler. Normally you aren't even aware of it. For the ARM GCC compiler, the function names have this form I show here. Now this AEABI term is a technical term related to compilers, and it's really not important here. So examples of these functions are this one, which multiplies two double variables, which is sort of implied by dmul. And this function, which converts a 4-byte float variable to an 8-byte double variable. And again, that's suggested by this name here. Now, for higher level operations that are in the math library, such as sine, log, exponent, the compiler handles them like any other library function. There's really nothing special it has to do. Now, when you're using these libraries, as I believe I mentioned before, you're responsible for choosing the correct function. The compiler isn't going to do this for you. So you have to know whether you want to call sine, which takes doubles, or sine f. Now, one thing the compiler will do is convert parameter types if necessary when calling a function. For example, it'll convert a float to a double in this case, where someone has called sine and passed it a float. That's poor code, but if you did that, the compiler would convert that constant to a double. Now in the coming slides, we'll look at the assembly or machine language code that is generated by the compiler for doing floating point. Now I know practically no one watching this will know ARM assembly language, but that's fine because we'll be just looking at key parts of the assembly language, and it really isn't that difficult. This is just straight line code. So here is the function that we're going to use. I won't go through this line by line here, but what the function does is uses floats and doubles in various scenarios. We'll be looking at the build output, the .list file that can be generated when you do a build. This is a great file to look at because it shows the lines of C code followed by the assembly language that was generated. Now I'm doing the build in the STM32 IDE, where this file is generated by default. It is located in the debug directory in the project workspace. If you're using makefiles directly, you would need to add the command to generate this file when you're doing the build. Now, the MCU we'll be using is this one right here, and it's located on a Nucleo board. And it has a single precision FPU on it. But we want to look at the cases with and without an FPU. And we can do that by controlling this compiler option -mfloat. And these are the two cases for using the FPU and not using it. And you can see you set the option either to hard or soft. If you're using the STM32 IDE, then there's a setting that controls this flag, and I'll show a screenshot of that on the next slide. If you're using makefiles, this would normally be part of the C flags. It was a little hard for me to find the setting in the IDE for whether you want to use the FPU or not. So I just took a couple screenshots to help you find it. And these arrows should help you locate where it is. And then here's the actual setting, and I think you have a pull down here or something where you can choose the different options. In this case, it's set to hard, which means you're going to use the FPU. And in this case, we set it to soft, which means you won't. So this is the first slide of the generated code. And we're looking at the case where the FPU is enabled. The lines of C I have put in red, and the important lines of assembler I've put in green. And these are really the only lines we'll be looking at. Before I get started, I'd like to just briefly explain the format of this file, the assembly lines in particular. So these numbers here are the addresses in Flash of where these instructions would reside. These values here is the actual raw machine code that the CPU or FPU will be executing. This is low-level stuff. And this is the assembly language, which is just a human-readable version of the machine code. So this is some getting started with the function. I will ignore that. And let's look at the first real line of code. And that is multiplying argf by itself and storing it in a_f, that variable. And argf is an argument of the function, and it's a float. And then this is also a float, of course. So we have a FPU that handles floats, single precision. And so this boils down to a single instruction. That does you could sort of read this. The V, I'm not sure what that means, but this is a multiply. F32 is a single precision float. So then the next line of code is multiplying argd by itself. You'll see argd is a double, but it's storing the result in a float. So the floating point unit can't do double precision. So this is going to have to be done in software. And that's this line of code here. BL stands for branch with link. And you'll see a bunch of those in this code. And you can just think of that as calling a function. And this is the address of the function. Fortunately, they put the name of the function in here. And so this is the function I showed you before that multiplies two doubles together. And it returns a double. And so because it returns a double, we're not quite done. We have to store that double into a float. So it calls another function, d2f, that's a conversion function to convert double to float. And then now the operation is complete, and it has it in the right format to store. So continuing on with the case where the FPU is enabled, we have this line of C code. And this is poorly written C code because this argf is a float, single precision float. We're passing it to sign, which expects a double and returns a double, but we're storing the result again in a float. So there's some extra code in here. First, to get this argument into a double, it generates code to call this function float to double. So now we have a double, and now it calls sign, and sign returns a double, but we have to store it in a float, so it calls a function to convert the double back to float, and then it can store the variable. Now here is the correct version of this, where we call signF, which takes a float and returns a float, and you can see it's a lot simpler, a lot less code. So continuing on, we have another case where there is a bad line of code and a good line of code. So here is the bad line of code. We have this floating point variable, and we're multiplying it by this constant, but we didn't put an F on the constant. So the compiler is going to assume that's a double. And as I mentioned, when you have mixed types, well, this is a double, this is a float, the compiler is going to promote this variable up to a double and do the calculation. So all the operands are doubles. But then it's going to get a double result, which it has to store back in a float. So the first call here, float to double, is converting AF to a double. It's then doing the multiplication. It can't use the FPU because it's a double precision. And then it takes the result of that and converts it to float so it can store it. Here is the proper version of that line of code. All we had to do was put an F in there, and look how much less code there is. And in addition, it's using the FPU to do the multiply, so it's going to be a lot faster. So here's the final line of code in that function, and this really isn't important. What I do is just add all these values and return that. And the reason I do that, compilers are very clever these days, and if you do some calculations often in a function, if you have the optimization turned on, I don't think it's turned on in this case, but if you do, and you do calculations and you never use the results, often the compiler won't even generate the code for the calculations because it doesn't need it. And in this case, I add all these variables together and return them. That forces the compiler to generate the code. So these are all floats, so we can use the FPU. There's 3 additions, and so you see 3 adds. And then this last one is sort of interesting. If you remember, the function actually returns an int. So what this is doing is using the FPU to convert a float, F32, to a signed integer, which is an S32. And that's the return value for the function. So now we're looking at the case where the FPU is disabled. And this is the same function, the same code. And I'm just going to show this first slide because the pattern is the same. Most of it is the same. I want to show you this line here where we're multiplying 2 floats together and we're storing the result in a float. And if you'll remember, when we had the FPU enabled, this multiply was done with a single FPU instruction. In this case, since it's disabled, the compiler inserts a function call to a routine in the C runtime library. In this case, it's fmul for float multiply. And that's the difference. In this case here, we're doing doubles, and since the FPU doesn't support doubles, this doesn't change. So when you have an FPU, a natural question to ask is, how much does this FPU improve my performance compared to just doing the floating point operations in software? Well, one way to answer that question is to use a computational benchmark, which is a standardized program used to compare the performance of hardware and software, such as compilers. So you might want to compare 2 MCUs or 2 compilers to see which one runs fastest. And maybe your application software isn't ready, or maybe it's just hard to test your application software performance, so you use a benchmark program. Now, the Whetstone benchmark is an old and simple one from the 1970s, and I think it even goes back further. It isn't so popular these days because it probably isn't very applicable to today's software. But I chose it for this course because it's well known to use a lot of floating point and it's small enough to run on an MCU. So the Whetstone is it's a small amount of code and it consists of 11 modules, each of which executes some type of computation. A module is just a block of code that is run some number of times in a loop. So there is this term Whetstone instruction, which is a unit of computational work consisting of running each Whetstone module a specified number of times. It was intended to represent typical computing at the time, but it is known for being biased towards scientific computing, and that's another way of saying floating point. Of course, that's what I want for this test, so that was great. Anyhow, the performance is stated as millions of Whetstone instructions per second, and you'll be seeing some of those figures shortly. So I got Whetstone code at this location here, and I modified it as follows. First of all, I made the C floating point type being used, float, double, or long double, easily configurable so I could measure each type. I also provided an option to only include the Whetstone modules that are primarily floating point. This makes it even more floating point centric, which is what I'm interested in. I ran the test with both the standard Whetstone and my modified version. So I then ran the test on 3 different MCUs, which I'll tell you about on the next slide. And if they had FPUs, I ran the test with and without the FPU. Now, for those of you who haven't watched any of my other courses, I have a bare metal software infrastructure with a super loop and various modules. To make this testing easy, I created a simple float module, and that module really just provides console commands to run the Whetstone test. So you can look at this module code, and you can look at that Whetstone code in the GitHub repo for this course. So here is the Whetstone benchmark code I got off the web, and I just want to spend a very short amount of time on this just to give you a sense of what it looks like. Here it is in C. It was originally written in Algol way back in the day. I don't think Algol exists anymore. I know it was also converted to Fortran early on. And this is the code. This code is the stuff I wrote to make it easy to convert what types you want to use. So if I want to use floats, this defines some macros that are then used throughout the code. And for example, sine gets converted to sine f if you're using floats. And then I'm just going to show a few examples of some of these so-called modules. And a module is just a block of code. And so module 1 is just doing some simple arithmetic, but it's doing it in a loop, and it's running the loop n1 times. And I'll show you one more module. Here's integer arithmetic, which we wouldn't be interested in. Here's trig, which we are very interested in. And again, it's running this loop, and this is module 7, and it's running it n7 times. So there you go. That's really all this Whetstone is. But you know, it doesn't have to be complicated to give us a sense of how much faster floating point is being done with the FPU. So here are the MCUs I used in the performance testing. So there were 3 of them. 2 of them were Cortex-M4s, a F401 and an L452. They both happen to be Nucleo boards. That shouldn't matter. And they both have single precision FPUs. And then I have this F103, which is a so-called blue pill board. It's definitely the least powerful of these because it has an M3 processor in it, and it has no FPU. And just some notes about the testing. All the boards, the firmware in all the boards was built using the default configuration from the STM32 IDE. So I didn't touch the clock tuning or anything like that. So it's whatever that IDE uses as the default configuration. I also used a debug build from the IDE. I didn't use the release. The release maybe has an optimized build, which would make things run a little bit faster. I'm really interested in relative results, so I wasn't too worried about that. And finally, I haven't tried to compare my results with, trying to find other people who have done Whetstone on these MCUs. I don't know if that's available anywhere. Like I said, again, here is my main objective was to learn about the relative performance between different MCUs, and more importantly, I think the how much effect the FPU has on the performance. So here are the measurement results. And I have two tables here. One is using the standard Whetstone, and one is using the modified Whetstone, where I left out Whetstone modules that did no floating point or very little floating point. So let's go back to the standard Whetstone and look at these results. Here are the three MCUs I just described, M4, and M4, and then this is the blue pill M3. Here's a test using double precision. The units of this are millions of Whetstones per second, and the FPU is not enabled. And so you can see these two are pretty comparable, and that M3 blue pill is significantly less. Here is where we went from type double to type float, single precision. Still, we aren't using the FPU, and as you would expect, I think there's, it runs, you get more Whetstones per second because 32-bit values are less expensive to calculate compared to 64-bit values. And again, this is, the M3 is quite a bit lower. And then here we keep float, but we turn on the FPU. And so now you see a big jump by turning on the FPU from float. And for the this M3 blue pill, there is no FPU, so I don't have results. And then here is what I call a FPU speedup factor, which is just this number divided by this number. And you can see it's around 4 times faster with the FPU turned on. So that's a significant speed up. Now if we go to the test with the modified Whetstone, again, here are the three CPUs. When we look at double, everything is faster, and it's just faster because I was removing work from the Whetstone benchmark. So it's doing less work, so of course it's going to have more Whetstones per second. But again, these are comparable, and the M3 is a lot less. Here is the same thing with floats, but not using the FPU. And then finally, here are floats, but with the FPU turned on. And this, you see these big jumps. And the speed up factor in this case, since it's more floating point intensive, is larger, over 9 times faster with this CPU, 6 times faster, 6.5 times faster with this other one. It would be interesting to explore, what exactly is the reason for the difference here. I don't know. It's just, at this point, it's just interesting to notice. And then it doesn't apply because this blue pill has no FPU. So here are the prompts for this lesson. I'll just display them for a second, and then I'll go through them one by one. Can you think of reasons why someone might disable the FPU, perhaps just for testing? Well, I could think of 2. You might have other thoughts. If so, put them on the comments. The first thought is to check if your application would run fast enough without the FPU. Because if that is the case, perhaps you could use a cheaper MCU that doesn't have an FPU. The second reason would be to check the relative power usage of using the FPU or not. It might be obvious whether using the FPU is going to increase power overall. I'm not sure. Power usage is a complicated topic, so it's something you could test. And of course, if the application runs fast enough without a FPU and it uses less power, you could go that route. To speed up your application, you replace the MCU with one that has an FPU, and let's say single precision. And you're careful to write your code so it's all based on type float. Will the flash image size increase or decrease? Well, I think the flash image size should decrease, and that's because all of the C runtime library functions for floating point, such as this one, are not needed and they won't be part of the flash image. FPU instructions, in terms of the code that's actually doing the floating point, FPU instructions take about the same space as calls to the C runtime library functions. So I would say that's about the same. The big thing is you don't need the C runtime functions. You have an MCU that has an FPU, but you forget to enable the FPU during initialization. The compiler is set up correctly, mfloat equals hard. What will happen when you do a floating point calculation? Well, because of that compiler setting, it's going to generate FPU instructions, but the MCU will be unable to execute them because the FPU isn't enabled. You'll get a fault of some type and an interrupt handler will be executed. Note that with the STM32 IDE, the default handler is an infinite loop, so generally speaking, things will just stop. I actually tried this. I wanted to be certain of my answer, and I found that this does indeed happen. You get this interrupt, and you'll get a usage fault. And in the Cortex-M, there's a thing called a usage fault status register that tells you more specifically what happened, and it indicated a no CP condition, which means no coprocessor. And this is the actual text from the manual. It says a Cortex-M coprocessor instruction was issued, but the coprocessor was disabled or not present. That's pretty clear. So here's a summary of this video lesson, which I'll go through briefly. First, we saw how floating point operations in C are compiled into assembly language using either the FPU or software libraries. Poor coding was seen to result in inefficient code. We found out that benchmark programs can be used to compare the performance of MCUs and see the impact of using an FPU. Performance was measured on 3 Cortex-M STM32 MCUs. The differences in performance of software-based floating point operation was seen due to the underlying MCU, for instance, Cortex-M3 versus Cortex-M4. Speedups as high as 9.2 were seen in use of the FPU. This is the end of this video lesson and the end of the mini course on floating point. I hope you found it useful, and thanks for watching.